This is Haggle Dune Field, located below the North Pole of Mars. It is also known as the Martian Morse code due to the linear and rounded formations of its dunes, which have the appearance of dots and dashes. Although normally it is possible to obtain information about the wind direction from the orientation and form of sand dunes, the complexity of shapes of the Haggle dunes makes it difficult to determine the direction of the forming winds. In the case of the Haggle dunes, it is theorized that a local circular crater, probably formed due to meteorite impact and filled with sand, has decreased the quantity of dune-forming sand. This in turn impacted the local topography, causing a change in wind patterns. The linear dunes were formed through the action of bidirectional winds acting perpendicular to the line of the sand dune, causing a funneling effect, directing the sand to accumulate along the linear axis of the dune. The round-shaped dunes were formed when the winds that caused the linearly shaped accumulations were interrupted. The round dunes are classified as Volcanoid dunes. However, the exact mechanism of either formation is still unknown, and this is the reason the area was chosen for imaging by the HiRISE mission. There are similarly shaped dunes in other locations on Mars, but the Haggle field provides better images of these shapes due to the uncommon characteristics of its topography. According to analysis of data from Mars rover, cracks, crusts, and ridges in Martian sand dunes point to the presence of water near the planet's equator as recently as 400,000 years ago. The findings also suggest that liquid water may have flowed in this region of the red planet much closer to the present than previously thought. Water in some forms does exist in and around Mars today. The planet's atmosphere contains small amounts of water vapor, for example. Mars also has water ice caps at its poles, and salty water may sometimes flow down hillsides and crater walls. During the Martian winter, water frost may form and water-based snowflakes drift through the atmosphere, turning to gas before they hit the ground. Scientists also think that bodies of water once existed on Mars's surface, but they evaporated billions of years ago. Recently, while studying the structure and chemical makeup of sand dunes in Utopia Planitia, a basin north of Mars's equator, the Mars rover team found depressions, ridges, and cracks on the surface that could not be explained by wind, which would have eroded the crust instead of creating these features. And frost made from carbon dioxide could not be the cause, since it wouldn't have formed that close to the equator. Instead, the team hypothesizes that water vapor condensed as frost and snow on the surface of the dunes, then melted when it mixed with sand. High temperatures during Martian mornings would have evaporated that salty water, leaving salt and minerals that combined with the planet's sand to create a hard crust. With more heat, this crust eventually cracked. It is estimated that the geological features of the dunes formed 1.4 million to 400,000 years ago, suggesting that Mars's climate at that time could have been more humid than previously thought. The geological features also indirectly show that liquid water could have existed when they formed. While the phenomenon was documented at one site, it should be applicable to a fairly large fraction of Mars's surface at similar latitudes, which suggests that there may be a wider distribution of this process on Mars than previously identified. Since Mars's atmospheric conditions today are similar to those of 400,000 years ago, the findings suggest liquid salt water may currently exist near the equator. As space agencies on Earth turn their attention to the red planet, such water sources would be crucial for future Mars-bound astronauts. Aptly named Mojave Crater in the Xanthi-Terra region, has alluvial fans that look remarkably similar to landforms in the Mojave Desert of southeastern California and portions of Nevada and Arizona. Alluvial fans are fan-shaped deposits of water-transported material. They typically form at the base of hills or mountains where there is marked break or flattening of slope. They typically deposit big rocks near their mouths close to the mountains and smaller rocks at greater distances. Alluvial fans form as a result of heavy desert downpours, typically thunder showers. Because deserts are poorly vegetated, heavy and short-lived downpours create a great deal of erosion and nearby deposition. There are fans inside and around the outsides of Mojave Crater on Mars that perfectly match the morphology of alluvial fans on Earth, with the exception of a few small impact craters dotting this Martian landscape. Channels begin at the apex of topographic ridges consistent with precipitation as the source of water rather than groundwater. This remarkable landscape was first discovered from Mars orbital camera images. Researchers have suggested that impact-induced atmospheric precipitation may have created these unique landscapes.